In the last video, we considered what happened when we had perfect squares, like x plus 1, the quantity squared, or x minus 1, the quantity squared. And we saw that those could be expanded to the quantity x plus 1 times the quantity x plus 1. That would be the long way of writing it, or the quantity x minus 1 times the quantity x minus 1. And so we worked on the pattern of looking at perfect squares. Now what we want to do is manipulate this slightly. So rather than have x plus 1 times x plus 1 or x minus 1 times x minus 1, we want to consider what would happen when we take the quantity x plus 1 and multiply it by the quantity x minus 1. So this is going to be slightly different. In fact, it's going to give us a much simpler pattern than the previous one. So using our distributive property and multiplying every term of the first factor times every term of the second factor, we can get a first term of x squared, and then we will get a minus x term, and then when we multiply 1 times x, we'll get a plus x, and 1 times negative 1 gives us a minus 1. So we can see what will happen if we try to add these or simplify this expression. We have a minus x and a plus x. So unlike the previous video where the middle terms doubled, we now have the middle terms canceling out. And so the result of this is that we get x squared minus 1. If we do the same thing with x plus 2 times x minus 2, we have x squared minus 2x plus 2x minus 4, which simplifies down to x squared minus 4. Once again, the middle terms end up adding to 0. If we do the same thing for x plus 3 times x minus 3, we get x squared minus 3x plus 3x minus 9, which simplifies to x squared minus 9. So what we started with is a pair of, an addition-subtraction pair of binomials. We'll call these addition-subtraction pairs. And when we distribute those, we end up with what is referred to as the difference of squares. Clearly, the x squared term is a square, but 1, 4, 9 are all perfect squares. So we have the differences of perfect squares when we do this. If we continue looking at the pattern, we can say, if we took something like 2x plus 3 times 2x minus 3, we could expand that and get 4x squared, and then we will have minus 6x plus 6x minus 9. So we end up with 4x squared minus 9. So in this case, the first square is the square of 2x, which was the first part of the first term of each factor. And the minus 9 is a perfect square of 3, which is the second term of each factor. So it works the same way. Let's just do one more example of this, and then we'll generalize it. So if I had 3x plus 1 times the quantity 3x minus 1, we would end up with 9x squared minus 3x plus 3x minus 1. So we would end up with 9x squared minus 1. So both of those are perfect squares. 9x squared is the square of 3x, and 1 is the square of 1. So we can generalize this and write all of these in the form ax plus b times ax minus b. If we ended up doing that, we could say that we will always get a squared times x squared. The middle terms will cancel, and we'll be left with minus b squared. And by the way, if you put the constant term first, b plus ax is the same thing as ax plus b, and if it was b minus ax, we would end up having b squared minus a squared x squared. So by switching the terms in the factor with subtraction, we know that switching two numbers around in a subtraction, like 5 minus 2 is the opposite of 2 minus 5. So the answer, when we switch those around, ends up being the opposite of the answer. Now, how does this help us? Let's clear some space and figure this out. Okay, so let's quick review here. Whenever we have the product of addition and subtraction pairs, when we distribute, we get the difference of squares. So let's look at a couple of examples that would allow us to go in the opposite direction. So let us consider the example x squared minus 9. Clearly this is the difference of two squares. So what we can do is we can write out that we have two factors which will be binomials. We know that x will have to be the first term of each factor in order to get a product of x squared. And then 9 is the square of 3. So if I say plus 3 and minus 3, the product of those will be negative 9. And because of the symmetry, we will have a negative 3x term if we were to expand this, and a positive 3x term that would cancel out. So this addition subtraction pair of x plus 3 is equivalent to x squared minus 9. Let's look at one more example. If I had 4x squared minus 25, both of those terms are perfect squares. 4x squared is the square of 2x. So I know that in my binomial products, or product of binomials, I should have 2x as my first term. 25 is the square of 5, so I know I need to have 5 as the constant term in both cases. And one of them has to be plus, and the other one has to be minus. Since multiplication is commutative, I could switch the factors around, and I have an equivalent answer.